Okay, and I see the thing. All right. So yeah, I think we can get started. Welcome, everyone. My name is Juan Carlos Lopez. I am the director of the Maple Leaf Teaching and Learning Center. And today I'm coming to you from Mi'kma'ki, so that's the unceded territory of the Mi'kmaq people. When I say this, it's because I'm in a journey of learning, and as a very good friend of mine and colleague says, I need to listen. My commitment is to listen and listen, and when I'm done listening, I listen some more so that I can learn the truth and move towards ways of finding a path for reconciliation. I also would like to acknowledge that that these lands have had people from African descent come in different ways for as long as recorded for 400 years. So, and again, the idea of mentioning this is to mention my commitment to listening and learning and finding a better future for everyone. So that's where I would like to start. So today we're having a very special, we call it a Maple Leaf host, because we are hosting someone from outside of our institutions. And Dr. Tom Mitchell came to us through Danny Silver, so who's a professor here at Acadia. So because of that, I'm gonna pass the baton to Danny so that he would introduce Tom, and thank you very much for coming.
Thanks very much, Juan Carlos. It's certainly my pleasure this morning to introduce Tom. It's morning for Tom, I guess it's afternoon for us. So I've been fortunate to know Tom for about 30 years through workshops and conferences, some sabbatical time at Carnegie Mellon in Pittsburgh, and as a co-author. And I also found it recently, he's also an avid weekend guitar player, so we've enjoyed that together. So Tom is the founder University professor at Carnegie Mellon in Pittsburgh, and he founded the world's first machine learning department. So his research is, as the title it indicates, is in artificial intelligence, particularly machine learning, but also in cognitive science and the impacts of AI on society. He's published widely, including a seminal book in machine learning, which I have still almost every one of my students look at. He has supervised over 40 PhD students and provided a range of service to the AI community, most notably as president of the Association for Advancement of Artificial Intelligence. This is the worldwide kind of AI organization. He did that from 2001 to 2003. He's contributed, his contributions in AI and machine learning are widely recognized. He's a fellow of the Association of Advancement of Artificial Intelligence. He's been that since 1990. Also a fellow of the American Association of Advancements of Science. He was elected to the United States National Academy of Engineering in 2010 for pioneering contributions and leadership in the methods and applications of machine learning. And he received an honorary doctorate from Dalhousie, actually, for those same efforts. And in 2016 was made a fellow of the American Academy of Arts and Sciences. He's been for some time playing an important role on U.S. congressional committees, has co-chaired different topics related to AI and its impact, and is currently co-chairing a U.S. National Academy study on AI and the future of work, as well as task force studying large language models. That's your ChatGPT type systems for special competitive studies project. His current focus, the topic of today on AI in education, is where he's worked closely with organizations in that field, computer learning environments to millions of students, including people in China and throughout the United States. So the title for today is Where Can AI Take Education in 2030? And Tom, it's over to you.
Thank you, Danny. What a nice personal introduction. I have to tell you all that even though Danny is only a somewhat better guitar player than I am, he has a way better singing voice. So if you get a chance, play with him. Okay, so today what I'd like to do, first of all, thank you for the opportunity to meet with you all. My plan is to give a talk that I hope will generate some discussion, and then we can have our discussion. So jot down your ideas and comments as we're going through this. The topic, as the screen says, is where can AI take education this decade? And really, the thesis of this talk is very simple. I'm convinced that if AI is ever going to make a real impact on education, this is the decade when it's going to happen. My argument is three parts. First, we've known for many years that human tutoring is extremely helpful to students. For example, way back in 1984, Bloom did a study where he compared students in a normal classroom, where there might be dozens of students being taught by a single teacher, to students who had individual human tutors. Nothing to do with computers here, but what he found was that the students who got the individual human tutoring, the individual attention, far outscored on the final test the students who did not. And so that's point number one. Point number two, happily, this decade, we finally, after decades of effort by a lot of people, we finally have computer tutors that have taught literally millions of students, which gives us the opportunity to apply machine learning now to the data gathered from that experience. And that experience is tremendous amount of experience. If you think of a human teacher, say, teaching a class of, even a big class of 30 students or 40 students, and having a 100-year teaching career, which nobody really gets to have, they won't come close to teaching 1 million students or to seeing the effect of what they're trying to do to teach. They won't gain that experience to become, they will gain a lot of experience to become a better teacher over time, but they won't come close to seeing 1 million students worth of teaching experience. So computers actually have more data to learn from than any human could get at a 100-year career. The third and final point is AI progress is accelerating in a very interesting direction. So these are the three arguments I give for why I think this is the decade for AI in education. And the rest of the talk is really just to go through some examples of that and where I think some of the interesting thesis topics are. If there are any grad students in the audience looking for thesis topics, I think it's a great research area. Okay, so let's begin by thinking for a moment. In fact, if we think about how computers can help with education, there are a variety of different settings. We could have one student on one computer. We could have students with computers, but a teacher sitting next to them. We could have teams of students working together with a computer watching and engaging. So there are different educational settings, and there are different AI technologies, notably these three that I think will have a special impact on education. So let's start by, and I'll primarily be looking at one-on-one student computer online education, partly because I think that's where things have changed so much and where change can happen rapidly. And I'll say that we've been working at CMU, my research team and I have been working with a California nonprofit company called CK12.org. Here's the homepage that they had earlier this year. And at that point, they had served over 200 million distinct students in the 15-year history of ck12.org. And they had students answer nearly 2 billion. Actually, I went back today to check, and now it's 2 billion plus questions that students have answered online, and 40 million total hours of student learning. So just to put this in perspective, I worked out the arithmetic, and 40 million hours is roughly 45 centuries. So just to give an idea of the volume of data of watching students learn that's available in these modern systems. So what does that data look like? It looks like this. This is actually data from a Chinese company called Squirrel AI. We have a data set from them which has 60 million student learning events, 60 million rows. And what you're seeing here is just the log data from one student in a 1 hour, 49-minute session, where they begin by taking a pretest. So each row here is describing a pretest question, whether they got it right or wrong, how difficult the question is, how long they spent on it, and so forth. And then after that, they watched some videos, read some text, solved some practice problems, watched another video, but they didn't finish it. They dropped out of the video partway through, solved some more practice. You get the idea. Then they did a post-test. Then they reviewed their performance on the post-test. So this is the kind of detailed log data that we can get from millions of students these days. And so if you're a machine learning person, you look at this data, and of course, the obvious question is, what can we learn from this? What should we learn from this? And I think I would suggest there are two primary things we want to learn here. The first is, let's use this data to infer for any given new student. We want to learn to be able to infer this knowledge state of new students at any given time. This is a problem that inside the field, people often call this knowledge tracing. But I think of it as the diagnosis part of teaching. You want to diagnose a student. What did they understand and not understand? And so if we're going to have computers do that, it leads immediately to the question, how can the computer represent the student state of knowledge? And the way that we do this, and many people in the field do it, is with a vector of probabilities. So I'll give you an example. In the biology course of CK12, there are roughly 4,000 questions that a student could be asked. No student ever gets 4,000 questions. It's more like dozens of questions that they get. But we represent the state of the student by a vector of 4,000 probabilities, where the ith entry in that vector gives our computer program's estimate of the probability that if we ask question I to the student at this very moment, the probability that they'll answer correctly. So we represent the state of the student by literally a set of probabilities of all the questions that the system knows about, and the probabilities that the student will correctly answer that question if we ask it now. So then we set up the machine learning problem of learning to estimate those probabilities for any given student based on what? Well, based on the history of the student. What is the log data for the student so far? And what are their demographics? Maybe they're an 8th grader in Chicago, and so forth, and what the question is. So we set that up as literally a logistic regression problem. And so what is the state of the art of doing this sort of thing? Well, we ran recently, Robin Schmucker is a senior PhD student in our group who led this study, but we got 4 different data sets, including that Squirrel AI one that we looked at a minute ago. But we got 4 different data sets that had each over 10 million logged items. And we trained for each of these using historical data. We trained our system to predict the probability that an arbitrary new student would be able to answer a question based on their log data so far, their history and demographics. And then we tested it on new students who had not been part of the training set. So, okay, how should we think about how well this works? Well, what I'm showing here are numbers called the area under the curve, but the way to think about this is the AUC is the fraction of times the program will be correct if we give it 2 questions, one of which we know this student can answer correctly because they did, and one of which they answered incorrectly. If we give it 2 questions, can it or can it not tell us which of these 2 the student answered correctly and incorrectly? Okay, and so if the program is just guessing at random, it'll be right half the time, because just you'd be right half the time if you guess. What we find is that if we simply keep track of which problems are most difficult, that is, what's the correctness rate across all students for this problem, then we can get up above 50%, up to these numbers, depending on the particular data set. But if we train our model to actually use that log data in the student history, then we get up to even better answers. So can this program perfectly predict what the student knows? No. Can I, as a teacher, when I teach? No. But these numbers give us a quantitative picture of how much better than random guessing we can actually do. And it shows that indeed we can do significantly better by personally customizing prediction based on the history of this student, what we've seen them do in the course. And this is true across several teaching platforms. So this is a pretty reasonable summary of the state of the art for diagnosing the state of knowledge of students. Okay, so that's one of the 2 problems. There are some things we had to do to sort of improve over earlier approaches. We use a pretty rich set of log data. We incorporate prior knowledge about which questions, what are the topics in the lesson, and which questions relate to which of these topics. So we know, for example, if 2 questions relate to the same topic. We also know prior knowledge about prerequisite. If you're learning math, you need to learn to add two single digits is kind of a prerequisite to adding multi-digit numbers. So we know our system knows things like that. So there's a bunch of techniques that we use to optimize the ability of machine learning algorithms to succeed here. Okay, I mentioned there were 2 key problems. I think learning to diagnose student knowledge data is the first of those. The second is the treatment problem. Once you've diagnosed the student, what's the right treatment? And so here the task is, at each decision point in the curriculum, what teaching action should the system take? Again, as a function of the student history and so forth. Now, one way we can think of this, we can frame this as a reinforcement learning problem in machine learning terms, where we can think at any given point in time, the state of the world is our estimated student state. That's what we just saw in the previous slide we produce. Then we can think of there being different actions that we could take for teaching. And we want to learn a policy for choosing actions conditioned on the state. And we want that policy to optimize some kind of reward. And here the reward that we want to optimize, of course, is the final learning outcome of the student. And so we want to learn, we want our machine learning algorithm to learn to choose the action sequence that optimizes the final learning outcome. So that's one way to think about the problem. Now, many people have actually tried reinforcement learning for these kind of educational settings. It tends not to work very well. The reason is that even though we have millions of students, we still have too little data, I guess that's the way to put it, to reliably do reinforcement learning. The reason is there's so many teaching actions you can take that if you think of the tree of sequences of actions you can take going forward for any given point, that tree is incredibly branchy. And so reinforcement learning, as a practical matter, doesn't work very well. So what we did was, what we tend to do, and what we did in the example I'm about to show you, is instead we pretend that each teaching action has an independent effect on the student, which is clearly not true. But now that reduces the amount of data that we need to reliably learn, statistically reliably. And it turns out to be a great trade-off. By pretending that the teaching actions are independent, we actually do learn teaching strategies that demonstrably improve learning outcomes. So let's take a look. Here's an example where we zoomed in on just one kind of teaching action, which is giving a hint. And so the question here is, suppose a student answers a question incorrectly. Like, here's a question. Integral monotopic proteins, it's a biology question. Integral monotopic proteins are permanently attached to the membrane from which of these four? The cytoplasm, one side, both sides, the middle of the membrane? Okay, that's the question. Suppose the student answers that incorrectly. It turns out we have a number of hints that have been contributed by different teachers over the years. And here are the hints. We could tell them, well, the prefix mono means single or alone. Or we could say the word integral means essential or necessary. Or we could provide this paragraph which has more information. Or maybe it's a vocabulary problem. Maybe they don't know what cytoplasm even means. Or maybe they don't know what protein means. That's in the question, protein. Maybe we should define a vocabulary term. So these are all reasonable hints. And if I ask you, which hint should we use? You probably don't know any better than I know. I don't know which hint's going to work best, but they all look reasonable to me. But if you had the experience of teaching millions of students, you ought to know. And so what we did was we collected data for 142 days from the CK12 website for 1,300 biology questions, for which there were typically half a dozen hints per question. So we had 7,000 total hints. In this way, we got 3 million student hint pairs along with the outcomes. And what do I mean outcome here? I mean, these students are asking, they go through a lesson, they watch some videos, read some text, and at the end, they have to answer 10 questions correctly, not necessarily 10 in a row, but a total of 10 questions correctly in order to complete the homework assignment that their teacher gave them on the CK12 website. And so we watch the outcome, that is, for students who got one or another of these different hints, we know how many of them completed the homework assignment correctly. We know how many of them answered future questions correctly. We know how many of them answered this question correctly on the second attempt. And so we applied our machine learning algorithm, and I can now tell you that among these hints, the one you should use in general is hint number one. And let's look at the data. Here we could give no assistance, or we could give these different types of assistance you see here. For hint one, for example, we have 986 examples of students who answered the question incorrectly, then got hint number one. Of those, 69% answered the question correctly on their second attempt. What's interesting is 93% of them completed the homework, eventually got 10 questions correct. And our reward function, which is, I won't go into the details why, but we did a lot of philosophizing and debate and discussion with the CK12 people to decide what we really should optimize is 0.4 times the reattempt correctness on this question, plus 0.6 times the final student score on the homework assignment. So it turns out that hint one is substantially better than the other approaches, except that the paragraph hint is also pretty good and actually does a better job at assuring the student will answer the question correctly on their second attempt. But it doesn't do as well in getting the student a higher score on the overall assignment. Okay, so you get the idea. You see what we're doing here. We're leveraging all this data from all these students to find out empirically what really works for teaching. And in the current version of, so I should tell you, we did this experiment and it worked so much better than the strategy that had been in place that CK12 agreed to just field this as the alternative policy for giving hints. In the first 2 weeks it was deployed, 66,000 students benefited from this. By now it's over 1 million, because here we are in November. So this is really having an impact. And now we've gone beyond biology. We're deploying this across the board in physics, earth sciences, chemistry, biology, and other courses on the CK12 website. Okay, so the take-home message of this first part of the talk is this. With today's platforms and the volume of student data that we can collect, it gives us a genuine opportunity to apply statistical machine learning to improve both the diagnosis of what the student knows and the therapy, the treatment of which teaching action to choose. Now, there's a lot more to be done. For example, in choosing best teaching actions, the only thing we've deployed so far is this hint giving strategy. There are plenty of other teaching choices that we make. Which video do we show? Which question do we even ask them? So forth. So there are many teaching decisions. But now in discussion with CK12, we're trying to generalize this approach, because you can see what we did for learning a hint-giving strategy can easily generalize to other kinds of teaching actions, provided we have enough density of data to get reliable empirical results. Okay, so that's part one. And I hope that I could stop there and you'd already be convinced that this is the decade when AI can make a huge impact on education. But I haven't said anything yet about natural language. And of course, I bet everybody on this call has experience with large language models like ChatGPT. And notice that everything I've said so far did not involve the computer even looking at the text of the question or the hint. We're just using the statistics of how many students got teaching action A or B, or answered question 59 correctly or incorrectly. There's no text analysis yet. So there's a whole nother layer of AI that we can bring to bear here. And let's look at that. So GPT-4 is the system that underlies ChatGPT. And I want to show you some examples that we've been working with as we explore how we can use GPT-4 to improve teaching. So here you see I gave GPT-4 a simple math problem, although I had a spelling error. What I meant to say is, suppose Mary drives from point A to point B at 100 kilometers per hour. Bill drives from B to A at 50 kilometers per hour, and both begin their drive at the same time. Will their paths cross? If yes, then where? Well, GPT-4 answers this question correctly, gives its reasoning. So they will meet at a point 2/3 of the distance from A to B, which is also 1/3. Okay. You get the idea. So it can answer this question. More interestingly, I now asked it, suppose a student answers incorrectly, that they will meet halfway between points A and B. What hint should we give the student? And its answer is, you could say something like this. Remember, they're not driving at the same speed, so they won't meet halfway. Think about who is driving faster and how that affects where they will meet. The faster driver will cover more distance in the same time. That's a great hint, if you ask me, because it really focuses your attention on the key ingredient of the question without giving away the answer. Okay, so the point of this is not only can GPT solve a large number of, not every, but a large number of, for example, math word problems and questions in biology as well. But it also can often come up with a good hint. Now, just to finish this example, one of the issues in online education is student dropout rates. If you have a human teacher sitting over you and you're not allowed to go home until 3 p.m. anyway, you're going to study. But if you're at home on a computer, you might just decide it's time to quit that and play video games instead. And so motivation and keeping students engaged is a key thing. So we got interested in the question of whether GPT could customize its output to the interests of individual students. I have a granddaughter who is a big Taylor Swift fan. And so I asked it, can you give this advice in the style of Taylor Swift? And it wrote the following song. And notice the chorus is the hint. You got to focus on the distance they travel before they meet and their paths unravel. Mary's speed is faster, that's a fact. So halfway between A and B is not where they'll land. And then it goes on to another verse and comes back to the chorus. Well, you get the idea. The point here is not only can the system solve problems and generate hints, but it can customize, in at least in this way, to particular interests the student might have. Okay, here's another example. In this case, a very simple problem. I bought 2 boxes of eggs, each contained 12. I gave away 3 eggs from each of the 2 boxes. How many remain? Okay, but here, the point of this example is that I asked GPT to rewrite that question to have a sports-oriented theme. And here you see it comes up with a basketball question. Instead of 24 eggs, now we have 24 basketballs for their training session. But each day before the training session, they give away 3 basketballs to a local youth basketball team. After 2 days, how many basketballs? So it's the same arithmetic, but couched as a problem, which hopefully would be of more interest to a kid interested in basketball. Or amusement parks, or birthday parties, or the Pittsburgh Steelers. Okay, so GPT can not only solve simple math word problems and generate hints, but it can rewrite those to specific interests. And it can generate hints along with those. Okay, What's another capability? Well, one of the problems with online education is just the cost of developing these systems. It takes a lot of human effort to build these systems. And so it's interesting to ask, to what degree could we just give GPT a textbook and have it read it and ask it to come up with the right questions that cover the material and test whether you understand? So here what you see is I said, please read the following text, then write some questions that would test a student's understanding of the text. And I gave it this page of text about the cell nucleus taken from CK12's material. So, and I just cut and pasted literally this web page. You can see, where does the DNA live? The answer. So I just cut and pasted this as part of the prompt. Its answer was this list of 11 questions. What's the main difference between prokaryotic and eukaryotic cells? How is DNA organized in the nucleus? What is chromatin and how does it differ from chromosomes? These are good questions. They really do capture the key aspects of the material. Then I asked it, of course, to answer the questions. Oh, I see, I overwrote. Oh, well, trust me, then it gave answers to each of these questions. So the take-home message here, excuse me, for this part of the talk, is that these natural language analysis by these very recent, just in the past year, large language models, we can use them to try to solve problems, generate hints, rewrite the problems and solutions to fit users' interests, and even to generate content from textbooks that are out there. Now, there's still a lot of research that needs to be done to figure out how to use these capabilities, especially given that they're not perfect. But I think you can see as well as I can that the potential here is very significant. And as these language models become more capable over the coming years, I think by 2025, we should have even more capable systems as well as some experience in how to try using these things. So let me give you one example of some very recent work. This is from a paper that's going to appear in next month's NeurIPS workshop on generative AI for education. And again, this is from our research group led by Robin Schmucker, our senior PhD student, but also Mung Zia, who's a postdoc, and Amos Azaria, who is a visiting professor from Israel at the time, this summer when we did the work, or started the work. And the idea is this. The idea of this system is, let's use GPT-4 to build an artificial student. And let's have human students learn by teaching the artificial student. Anybody who's a professor understands very well that the best way to learn a material is to have to teach it. And if you don't teach it right, those annoying students will ask you questions until you have to figure it out yourself. So we thought, why don't we use GPT to build an environment where human students, we'll call them the humans, teach a student bot, which is actually GPT-4. So that looks like this. And I'm going to do something a little gutsy, which is give a live demo instead of, okay, good. So let me stop my screen share and go to a different screen. Okay, so I believe you can all, excuse me, listen to my voice. I believe you can now all see the screen. And let me reshape this a little to be more like the the screen you've been looking at. So here's some text that the human will read and hopefully learn about organelles in eukaryotic cells. But over here on the left is the student bot. This is secretly GPT. And it says, "Nice to meet you, teacher. I'm the human, I'm the teacher. I am Ruffle. Thank you so much for helping me study biology. I love to learn." And then it says, "I am eager to learn about cell biology. Could you please explain what the phrase form follows function means in this context?" And if you look over here, you can see there's some text about form follows function. So if you had read that text, you'd be in a position to say something like, sure, it means that biological organs are shaped in, oops, not that good of a typist, in a way that supports their function. Okay, so now let's see. "Thank you for your explanations. The structure of biological components is designed to support the specific functions. Could you please provide an example to illustrate this related to cell components or organelles?" Okay, so now that's unfortunate. Now I have to actually read. So I haven't really studied this, so I'm just going to say ribosomes are shaped like DNA. This is false. Which supports, I'm just making this up, supports their function of reproducing DNA. Okay, so I'll say that. I may have killed the demo. Oh, okay. Okay, so now it says revision required. And now this other bot, which we haven't seen yet, which is the professor bot. So there are actually two bots here. There's a student bot, which I'm teaching, but there's also a GPT-4 based professor bot looking over my shoulder. And it says to me, "It seems there's a small mix-up in your explanation. Ribosomes are not shaped like DNA, but rather they're responsible for protein synthesis, translating the code provided, etc. Could you please revise your response?" So you get the idea. And we could go on, but it's probably not necessary. The point here is that this is a learning environment where I, the human, am learning cell biology by teaching a student bot while a professor bot looks over my shoulder. And because of the progress in AI in the past 12 months, we now can build bots that actually understand the natural language communications that I'm giving to the student bot and understand the text of this lesson well enough that they can guide me through the process, spot when I'm making a mistake, give me advice about how to fix that mistake. Okay, so I'm going to stop share and go back to the slides. You get the idea. So what's going on there? Actually, what's going on is there's this conversational system, which we just saw. The student bot has a tutoring script. It has been told from somewhere, we'll get to that in a second, what are the key concepts that me, the human, should teach it. And then there's a professor bot, which also has read the material and can chime in. So that's the system. Now, how do we create that chatbot? Well, these are the instructions we gave to GPT-4 to define the student bot. We said to it, you are an enthusiastic 18-year-old student who is trying to learn. You need the user, who is the teacher, to slowly teach you all the topics in the material. You have access to a list of topics, but not to the material itself. You must learn one topic at a time. This is the list of topics you found from the internet that you need the user to slowly teach you. And then here we insert a tutoring script, a list of questions that this student bot should make sure the human teaches it. And then we say, you need to learn very little at a time. Ask the user, who is the teacher, to teach you the material little by little. If the teacher gives you the answer, you must A, show appreciation, B, insert a smile, and then C, ask a follow-up question if you need more information about the current topic, or ask a question about the next topic. Do not move on to the next question before getting an answer for the current question. If the teacher doesn't know something, tell the teacher you will be thrilled if the teacher can check it and get back to you. When all the topics are covered, thank the teacher and say, I've asked all the questions. That is literally how we program GPT-4 to act in the way that you just saw. Similarly, we program it to create a different instance of a language model to be the professor. And this one, we tell it in a similar set of instructions, step 1, determine if the teacher conveys important information relevant to the student's question. If yes, provide encouragement. Determine if it contains factually incorrect information. If yes, gently point it out. If the teacher does not know the answer, encourage them to look at the learning material, and so forth. So this is literally how we program GPT-4 in natural language, our requests for the kind of behavior we want it to exhibit. Okay, final point here is I mentioned that this was the conversational system. It requires that the student be given a tutoring script, a list of questions along with possible confusions. Where does that come from? Well, in the old days, it would come from a human teacher figuring out what are the questions. In this case, in this system, it actually comes from another GPT-4 based system that reads an online ebook, generates the set of questions and solutions and expectations about the level of detail that the human should provide when teaching the student bot. How does it do that? Well, think of the examples we just went through before this demo. We went through a bunch of examples where, for example, I gave some text to GPT that was about biology, and I asked it to come up with a set of questions, and it showed us those 11 questions, which were in fact a good capture of the key topics in that text. All right, so that's the idea. Let me just show you. I'd rather spend the time on questions. I'm not going to show you this video, but I'm just going to say what we've seen so far, I think, is a pretty interesting set of research opportunities for exploring how AI can really change the way that students learn from computers. Beyond that, another direction in which AI is advancing quickly is perception of the external world. And so there's another thread of research that I think needs to be done, where instead of assuming the student will always be on screen, on the computer screen, interacting, sometimes we'll have students interacting in the real world and computers watching them and becoming a third player in what would otherwise be a two-player experiment, in this case about physics. So that idea that AI will also provide opportunities for computer-based teaching assistants to watch and interact in the physical world, not just on the screen, is another direction of research that's important. But what I really want to do is finish up so we can have a discussion. So let me just say, think about putting all this together. My dream is to build a teaching system that, like CK12 system, teaches millions of students, but unlike today's CK12 system, continuously improves its ability to teach. I want it to be a never-ending learner where its task is to learn to teach better as a side effect of being used. And that could include components like continuous generation of new content, new questions, new hints. Some of those could come from the AI system. Others could come from the questions the students ask of the system. And if there's a question that thousands of students ask, then probably that's a central question that ought to be added to the curriculum. Can learn which teaching actions work best, track each student's knowledge state, add conversational interactions between the AI, the student, and the teacher, support both on-screen and off-screen learning activity. So I think what I'm hoping in the coming few years, we'll start to see systems that combine all of these AI and learning capabilities to give us systems that really do become never-ending learning teachers. So let me end there. Again, if you're a graduate student looking for a thesis, take a look in this area. There are an awful lot of opportunities. And I can't stop without pointing out that there are a lot of non-technical issues that are going to have to get solved here as well. So thanks for your attention. Looking forward to comments, questions, discussion. I don't know how to run this.
So I will help you with that, Tom.
Okay, thanks.
So we can ask questions just by raising your hand or unmuting yourself, or you can type on the chat and I can read the question. We have about 5 minutes, so you know, first come, first serve. I see a hand, I think it disappeared. Okay. I look up how to pronounce your name.
Wojtek.
Wojtek. Go ahead.
Hi. I don't know if you can see me. Can you see me?
Mm-hmm.
Can you hear me? Okay,
yes.
Fine. I'm using a cell phone which I never used with Zoom before, so that's why I'm not confident with that. Thank you very much for the presentation. It's terrifying, of course, because mostly because of the bleak future of teachers, and that could be replaced by machines who will be actually more effective. Or at least this is one of the possibilities. But I'm just wondering, in terms of teaching, one of the elements that we are doing is not only to find the best way to teach a content, but also diversify the way we teach it, and also diversify the way students can show us what they've learned. So it's not about the question being right or wrong. It's rather to, at this point, and with the use of technology that we have, is rather to find ways that would allow to maximize the amount of people who will be able to learn, and maximize also the different ways to meet students' way of learning. And I'm wondering if you are taking that into consideration while working on those programs, or is it always about the most effective way to teach, and that will be based on a majority?
Yeah, that's a great question. I agree with the point of your question, which is that I hear it as kind of twofold. One is different students learn in different ways. And second, we actually may want to diversify the content that we're teaching. One thing that I've learned as I work in this area is that there's a huge difference in how you want to teach as you go from one course to another. For example, if you want to teach algebra, there is a truth, and you want to teach the correct way to do algebra. If you're trying to teach social studies, what you want to do instead is teach people to think about what the historical facts are and how they want to judge it themselves. And there isn't, in some sense, I mean, there's a historical truth, but then your opinion about what was the correct thing to do is not a single thing that holds across everything. So I would say right now, at this point in history, these online systems are best for the first kind of course. They're best for math, science, and so forth, where there is a single ultimate truth, and we want to teach that. But at the same, well, and when I showed the example of learning to choose the right hint for the student, I showed that as, let's find the hint that works best on average across all students. But in fact, we're now experimenting with a more refined approach that learns to choose the hint based on that individual student's history. So I do agree that we want student-specific teaching, even if we're in these kind of materials like biology and math. But I'll just mention quickly that if you look at Khan Academy, which is another online website, one of the things they do that I find fascinating that gets to your question is they have a way of trying to teach essay writing to students or story writing to students. And what they do is if the student is stuck, they take turns. They will write the next sentence, and then you write a sentence, and then they will try to write the sentence that follows that. So those kinds of learning environments, which we had never seen before because we never had the natural language competence in AI to even consider doing that, now is suddenly something that's, you know, a viable thing to consider. And Khan Academy is experimenting with that with real students these days. So I think that kind of opens up a lot of interesting things in terms of diversity and teaching about judgment as well as factual things.
So we are lamentably sitting at 1 p.m. So this is where, you know, if you have to go to your next thing, by all means. And I want to formally thank you, Tom, for doing this. Now, having said that, I can stay a bit longer if there are other questions. What I will do is that I will stop the recording now. And if you can entertain that, Tom, to stay a bit longer, we can answer a few more questions.
Yeah, I'll be happy to stay longer. And I'll also just say I just chatted a link in case you want to download the slides. They're available at that link. Excellent.
So I will stop the recording, and then we can hear more if we have more questions. Thank you very much, Tom.